Welcome back everyone to coding part 2 for k-nearest neighbors. Specifically, how do we actually choose this number of neighbors or k-value? And we're going to be exploring two ways. One is the elbow method, and two is just a full cross-validation grid search. Now, in this full cross-validation grid search, we're actually going to be introducing a new object and class from scikit-learn known as a pipeline. And a pipeline object in scikit-learn is really a method of convenience because it can set up a sequence of repeated operations. For example, we've already set up a scalar class call and then fit and transform based off that scalar, and then we also created a separate model, and then we fit that model and then perform predictions from the model. The pipeline object allows us to just actually set these up in sequence, so then we only need to call the pipeline instead of having to repeatedly call the scalar and model separately. So again, pipeline is really more of a convenience. It's not a must use, but later on you'll see that it becomes a lot easier to set up a pipeline for repeated workflows than having to do everything separate calls. Let's go ahead and explore all of this by heading back to the notebook. All right, here I am at the notebook where we left off last time. We previously created a classification report, and recall this model that we created only used the single nearest neighbor. Let's go ahead and now explore multiple neighbors. First, I want to show you the kind of simplest way to do this, which is the elbow method. Considering that we already have a scaled data set and we also already have a model, what I could do is just keep running this and keeping track of my test error, essentially 1 minus accuracy, and choose the k-value that minimizes this test error. So what I can do is just a for loop here. So I can say test error rates and set this up as an empty list. And then I will say for k in range, and let's go from 1 to 30, and it will actually go up to, but not including 30 here. I can say knn model is equal to, and I will create a new k-neighbors classifier where the number of neighbors is equal to k. Then after I create that model, I will fit this particular instance of the model on my scaled x training data and the corresponding y training data. And then after that, what I'm going to do is I'll simply create the predictions. So I'll say my y-pred from the test is equal to knn model predict. There we go, predict off the scaled x test data. So now that I have my predictions, I'll simply get my accuracy score or my error. So how do I actually do this? Well, the simplest way to do this is just say from sklearn.metrics import accuracy score. Recall that accuracy score essentially just returns the accuracy. So that means if I said, what's the accuracy score between y test and y predictions for my previous model that I already created, it's going to say the accuracy is 89.2%, which means my error is equal to 1 minus my accuracy, where my error is essentially how many points am I getting wrong. Recall from our discussions on classification metrics, accuracy is reporting the percentage you're getting right, which means 1 minus accuracy is going to be the percentage I'm getting wrong. So what would be nice for the elbow method is to basically see what k-value is minimizing this error term. So what I will say here is that my test error is equal to 1 minus accuracy score between y test and my y predicted test values. And then finally, we'll also say test error rates, and I'm going to append this test error. So that way, at the end of this, I should have a list of test error rates, which is essentially a number that looks something like this, like a 10% error, 9% error, etc. And I know that the actual kind of index location is going to be related to the k value. Keep in mind, it's technically going to start at index 0, while my k's start at 1. Obviously, you don't want to start at k is equal to 0, because that will give you an error. You have to choose at least a k equal to 1. So if you run this, keep in mind, depending on your computer, this could take a while, but we have a really simple data set. It should be almost instant. And then what I can see here is my test error rates. And what you'll notice here as we explore these test error values is, in general, for most problems, not every single one, but in general, as you start with some low k values, you're likely to have a higher error rate. And then as you increase k, you're essentially gathering more signal, more information, and you'll start to see it drop down until eventually, depending on your data set, it really starts to level off, where introducing more neighbors doesn't really actually help your classification error go down. And in fact, what could happen, depending on the data set, is as you go too large of a k-value, you're just considering way too many points, and then your error could start to spike. So in general, for k-nearest neighbors, you tend to see either a leveling off or a leveling off and then later on a spike, depending on how large of a k-value section you're checking. In fact, let's actually see this visually by saying 𝒊𝒕_plot, and I'm going to plot out the range of values, that is 1 through 30, on the x-axis, so essentially the k I was considering, and then we'll plot this against the test error rates. And just to make it clear, we'll say 𝒊𝒕 y label is my error rate, so how many or what percentage am I getting wrong, and then 𝒊𝒕 x label is going to be my value of k, so the number of k neighbors being used. So we can run that, and I can see essentially the behavior we just described, where for just a few values of k, we get kind of a larger error. It starts to go down, and notice that eventually it starts to get kind of noisy and level off. And I've noticed that students who are just beginning to understand k-nearest neighbors are really tempted to choose the exact perfect k value where you get the minimum. You'll notice for this particular train test split, we started to get a minimum around maybe 22 as our k value. However, you always want to consider the trade-off between how complex your model is versus how much error you're actually reducing. You'll notice that pretty much right after k is equal to, I would say, around 6, you're really not improving your error that much for how many more neighbors you're considering. We only go from an error rate of about 6% to maybe 5% when we jump from somewhere around k is equal to 6 all the way to k is equal to 22. So adding in maybe almost 15 more neighbors to consider, is it worth just dropping your error rate by 1%? I would say that really depends on your context and situation, but it is definitely something you should be considering of whether or not it's actually worth it. Is it worth it to add the complexity of your model to consider 15 more neighbors when really just considering 6 pretty much gets you almost the exact same error performance? Especially on this particular train test split, you don't actually know if on another train test split, this leveling off effect would be even more pronounced. So what we could do then is actually perform a grid search with cross-validation to see whether or not it's worth it to jump that high to something like 22. Maybe it's worth it maybe just to go to like 15 or 18, 19, etc. Maybe somewhere around this range instead of trying to optimize for what this particular train test split had at around 22. Let's go ahead and explore this. What we're going to do is we'll actually set up a pipeline. That way, I can have my scaler and my k-nearest neighbors already set up so I can feed them the raw unscaled data, and that is xtrain, xtest. I'm still going to do a split, but the scaler is going to be inside the pipeline. So how do we actually set up our pipeline? Let's explore this. So right now, we're going to set up our pipeline to later go into a grid search using cross-validation. So let's check this out. What I'm going to do is for my pipeline and for my grid search, essentially, I set up the very basics class calls. So I have an instance of my standard scaler and an instance of k-nearest neighbors that I'm simply going to call KNN. So I have a k-neighbors classifier. Everything is the defaults. And you should note here that what we're going to do actually requires very specific string codes. So if you check out KNN get params dot keys, this should return back a set of dictionary keys for all the parameters you can affect inside k-neighbors classifier. And keep in mind, if you accidentally use the wrong string code, depending on how you set this up, you could get an error. So something to really note as we're kind of typing along here is you should be using the exact same string codes and the exact same pairings I do. In fact, I'd highly recommend that you use the exact same variable names as well, because the pipeline object is quite picky as far as matching everything up. You can imagine, since you're passing in many different class calls, it needs to know exactly what variable name matches with what string code. So what we're going to do here is, after you create your scalar class and your model class, keep in mind later on you could switch out k-neighbors classifier for another classification model, it's time to set up your operations. And the way this works is we create a variable called operations, and it's a list of tuple pairs, where you provide a string code which is going to match the variable name chosen here. So the first thing I want to do is scale incoming data. So I'm going to call the string code scalar, and I pass in the variable for my scalar object, which is also called scalar. These two should match pretty much exactly, except one is your string that you're going to reference later, and then one is the variable name. So what's the next thing I want to perform operation-wise? After I've scaled the data, I'm ready to actually create my model and fit my model. So I will say KNN, comma, KNN. And again, this string code should match up with the variable name here. And those are my operations. Obviously, later on, we're going to introduce more and more complex sequences of operations for other models, especially for things like natural language processing. But here, we get the main idea that I can create these tuple pairs of operations, and they should be in the order you expect them to occur. I expect scaling to occur, so it's at index 0, then index 1 will occur next, index 2, and so on. Now it's time to set up our pipeline. We say from scikit-learn.pipeline import pipeline for capital P. And then to create my pipeline, I'll say pipe is equal to a pipeline object. You'll see the pipeline objects take something called steps, which are essentially the operations or transformations you want to do. So for this, we simply just pass in operations. So here are the steps I'm going to be taking in my pipeline, what I like to call operations to be performed in my pipeline. And now we'll say from sklearn.modelSelection import 𝒘𝒊𝒕𝒉. Keep in mind, we've already experienced how to use 𝒘𝒊𝒕𝒉, and we've performed 𝒘𝒊𝒕𝒉 on data that did need to be scaled. So we would scale everything first, and then perform 𝒘𝒊𝒕𝒉 on the model. This is just another operation you can choose. Keep in mind, you don't always have to choose pipeline. In fact, anything that can be done with a pipeline, you should be able to do without a pipeline. It just requires kind of more setup and more code, and you're keeping things separate. And in some cases, maybe you do want to keep things separate. But right now we can see that it's going to be pretty convenient to be able to just call this little pipe object and have it both scale and train a model. So we have our 𝒘𝒊𝒕𝒉 here, and what we need to do is essentially decide what k values do I need to work with. So I can say k values as a variable is equal to the list of range, and let's go ahead and say from 1 to 20 or 1 to 30. Depending on how large of a range is, this may take a while, so keep that in mind. Recall that we're not just checking these k values, we're actually performing cross-validation for every single one of these k values. So you're doing a lot more work here, computer-wise. Okay, so I have these k values that I want to test out. It's just a list of different k values I want to set up. So I should set up my parameter grid. And this is where you have to pay really close attention to the naming criteria and key name that we're going to choose for this parameter grid. Previously, we've been able to do something like this, where I just said, hey, my number of neighbors that I want to edit is going to be equal to here k values that I want to explore. So typically, when we've used grid search in the past, we've actually set it up like this. However, we're not going to be able to do that with 𝒘𝒊𝒕𝒉 if I use a pipeline. The reasoning behind that is because 𝒘𝒊𝒕𝒉 is going to take in this pipeline, and if you want to search this parameter grid, n_neighbors, 𝒘𝒊𝒕𝒉 doesn't actually know if n neighbors goes with this particular operation of scalar or this particular operation of k nearest neighbors. So this is why we have to be extra careful when naming our operations and also naming our parameter grid. So pay really close attention to this schema and criteria that we have to follow here. And we actually have kind of a step-by-step on how to do this inside the lecture notebook. So definitely check out the lecture notebook, but I will copy and paste the general rules to follow right here from the lecture notebook. And there's a Stack Overflow post on this. Essentially, for the parameter grid, this is what we have to do. It's the chosen string name plus 2 underscores plus the parameter key name. So what that would be is, what is our chosen string name? Well, if we look back up here, it's this string name for the operation. This is why we so highly recommended that you keep this variable to match this string code. So you'll always have these matching. That way you have this actual string code here. So this is the operation or step I'm referring to. So let's go ahead and kind of clear out this because this won't work. So I have to check the chosen string name. So that is KNN. It comes from this. That way I'm telling, hey, 𝒘𝒊𝒕𝒉, the actual step I'm referring to for this parameter is KNN. Then you add in 2 sets of underscores. So keep in mind, it's not just one, it's 2 sets of underscores. So then I'm going to say underscore underscore, and then you add in the parameter name. So that will be n underscore neighbors. So I copy that and I go ahead and place that in. Notice there's an underscore here between n and neighbors, but that's just because k and n happens to have that parameter. So the generalized way is your chosen string name for the operation, 2 underscores, and then the parameter you want to kind of set up the grid for. So that's why we specifically have to have the key value like this. That way grid search CV can know what number of neighbors is referring to. It's referring to the k and n string code, which refers to this k and n variable, which refers to our kneighbors classifier. Obviously, it's a little more complex to set up a pipeline, but that comes at the cost of kind of work up front in order to later on just conveniently call and save your pipeline object. So keep in mind, if this kind of was a little too complex for you, go ahead and read the lecture notebook where we separate out all these steps, step by step. But the main thing to consider here is when you're setting up your parameter grid for a pipeline in combination with a grid search CV, you'll have to choose the string code, 2 sets of underscores, and then the specific related parameter for whatever is working with this string code. So then I say colon k values. Okay, so luckily for us, this is actually a very simple parameter grid, but obviously you could keep adding in more things. So if I wanted a new k nearest neighbors distance metric, I'd have to say, okay, first off, help on k nearest neighbors, what's the actual parameter called? So I have to check these parameters. So I can see, okay, my parameter for distance is metric. So how would I actually set up a different metric to test out? I have to say, okay, k and n underscore underscore metric, and then set up a list of metric values like Euclidean distance, Minkowski distance, or Minkowski distance, etc. So keep that in mind that it's just the name of the string code that is related to this operation, 2 underscores, and the name of the parameter. That way grid search can know what you're actually referring to in the operations. So we have our parameter grid ready to go. And let's set up some cells here. So my parameter grid's ready to go, my pipeline's ready to go. It's time to set up my grid search. So I'm going to say foo underscore CV classifier is equal to grid search CV. I'm going to pass in this pipeline object, pass in the parameter grid, and then choose some number of folds for cross-validation. Let's go ahead and say 5. And then finally, what do I want to score by? We were scoring by test error. So that's essentially the same thing as accuracy, because either you're trying to maximize accuracy or minimize the test error. So just say scoring is equal to accuracy here. So now I have my full CV classifier, has the pipeline, has the associated parameter grid. Let's go ahead and fit it. So I simply say full CV classifier, and I can actually fit this on X train and Y train. So here's the really cool part. I don't need to actually scale the data myself anymore because that scaling step is within the pipeline. So the pipeline will actually scale the data correctly. And keep in mind, it's actually doing this kind of in an intelligent way. It will scale correctly according to the cross-validation folds in order to only fit transform to the training set of that particular cross-validation fold, and then only transform, not fit, to the test portion of that cross-validation fold. So kind of keep that in mind that it's actually performing this correctly for us. And you can check out the lecture notebook for a deeper discussion on that. But main thing you need to know is you can just now pass in X train and Y train. Okay, so go ahead and fit this. Keep in mind, this is going to take a while depending on your computer because it's checking out the number of neighbors with this 5 cross-validation folds. So it's essentially checking, or it's running something 5 times 19 or 20 actually in this instance. So it just ran 100 different operations. Okay, so I just fit my full CV classifier. Let's go ahead and check out the best estimator. So I say full CV classifier, and then what I'm going to say is best estimator, and I can actually then say dot get params, run that, and it returns the parameters that it chose here. So you'll notice it says here k and n underscore n neighbors 14. So it decided on 14 to choose for its best classifier. And what's interesting with the parameters here, you can see the same setup we just talked about. The parameters of the scalar and are also here, and then 2 underscores, and then the parameter name. So these are the parameters, not just for our model, but actually for everything, right? It's the parameters for the scalar as well as the parameters for k-nearest neighbors. It's the parameters for the entire pipeline that the cross-validation process found. So we have this full classifier CV ready to go. Let's go ahead and now actually run it. So what I could do is, if I'm setting up a final model, I could retrain everything on it. And again, it's kind of up to you how you want to do this. You could set up a new model that uses k specifically equal to 14, or you could just call full CV classifier and then predict on the X test set that was kind of this holdout test set. Recall that we only did our cross validations on X train. You'll notice for full CV classifier, I do not need to scale the test data. The scalar is already inside that pipeline. So I can say predict X test, and if you run this, you should see a bunch of ones and zeros as our predictions. So let's go ahead and scroll back up here and say the full predictions equal to this, and let's run our classification report again. We will say print classification report against Y test and our full predictions. Run that, and you should see this performance, and note the performance here is now actually better than what we had before. So obviously k is equal to 1 is probably too simple of a model, but we didn't have to go all the way to something like k is equal to 22 as we saw in the elbow method. Here, after testing many different k's against different cross-validation folds, we saw that overall k is equal to 14 looked to minimize that error. And we're getting an accuracy now of 94%. And keep in mind, everything we already know about saving a model as a pickle file also applies to this full CV classifier. So something else we could do is predict a single sample. So let's say I have someone else for a new gene expression, and I know their gene expression is something like 3.8 or 6.4, etc. So I could say new patient is equal to, and let's go ahead and say they have gene 1 score of 3.8 and a gene 2 score of something like 6.4 or something like that. So I have this new patient and I want to figure out, do I report whether or not they have cancer? I could just take this full CV classifier and I can say predict. And notice I can predict and predict probabilities, which is quite nice. So I'll say predict new patient, and I predict that this person does not have cancer. And what I could also do is say full CV classifier, predict probabilities on this new patient, run that, and pretty much I'm 100% sure that this person won't have cancer. And the way we can kind of get a probability from number of neighbors is by comparing the votes per neighbor. So if we had an almost split vote, we'd have a different probability there. But you can see here that all 14 of the nearest neighbors were voting for class 0, which is why we have 100% probability for class 0 here. Okay, so that's it for this lecture. I hope you found pipeline having a lot of potential for future use. We'll be revisiting it again in the future for more complex tasks. Thanks, and I'll see you at the next lecture.